Hello everyone. So let us continue the problems on cantilever beams using the conjugate beam method. So let us solve the different types of problems on cantilever beam. So in the given question, you're supposed to find maximum slope and deflection. And in addition to this, you're also supposed to find slope and deflection at B. So you have to find, obviously, because it's a cantilever beam, maximum deflection and slope will be at C, that is free end. And they've asked us to find deflection at B also. Okay, so after this, once the problem is given, draw the deflected shape of the beam. That A, it is zero deflection, no rotation because it's a fixed support, and it goes on deviating, and it is maximum at C. So at C, draw a tangent, so that would be theta C, and the vertical displacement is delta C. Okay. In addition to this, you have to also find at this portion, that is delta B and theta B. Okay, so once you draw the deflected shape of the beam, then you have to draw M over EI diagram. So M over EI diagram would be again same. First draw the bending moment diagram, then divide the ordinates by EI. So at A, so bending moment at C is 0 because it's a free end. Then bending moment at B would be 10 into 1.8 into 1.8 divided by 2. W into L by 2. So it is 10 into 1.8 into 1.8 divided by 2. So that would be 16.2 kilonewton meter. Similarly, bending moment at A. Okay, so now bending moment at A, you have to find out between A to B there is no load. So what you have to do is, again, this UDL 10 into 8, 10 into 1.8 into 1.8 divided by 2. So you're at this level. Next, because you're finding bending moment at A, you have to add this 1.2 here. So now 10.10 into 1.8 is the load. Then the complete distance is 1.8 divided by 2 plus 1.2. So when you solve this, you'll get this bending moment is maximum at A. After this, after drawing the M over EI diagram, then you have to assign the conjugate supports. So end A is fixed, so end A becomes free. Similarly, end C is free, so end C, because it's free becomes fixed. So just draw the fixed support here and then show the vertical force here. First, we are more interested in the vertical shear force. So this complete area is acting downward. The area of this bending moment diagram is acting downward. To stop this, there is a shear force acting upward. All right. So now, so first let's start calculating the maximum slope and deflection. So obviously maximum slope and maximum deflection is at C because it's a free end. So use the formula theta C first. Maximum slope, maximum deflection. So maximum slope theta C in real beam is equal to shear force at C in conjugate beam. Sorry, I've written here VB. It is actually VC, because which is acting exactly at the below C. So it is VC. So if it's acting here, that would be VB. Okay. So now theta C in real beam is equal to shear force at C in conjugate beam. So shear force at C in conjugate beam means left side consider all the loads which is acting downward. So there are two areas acting here. Okay, first take this area. Now see here, when you're drawing this bending moment diagram, because there's a UDL between B and C, so you'll have a parabolic curve here. All right. So it is now 1/3 of base into height. So it is 1/3 of 1.8 into 16.2 over EI. Then this is a trapezium. Now here, this is trapezium. Either you can treat this as trapezium, or to, if you're more comfortable with dividing this into a rectangle and a triangle, that would be easy. Now here, there is no load. That's why this line should be a linear line. This is a parabolic line. This is a linear line. So what you can do here, you can split this like this. 16.2 up to this portion, and whatever is remaining, this is a triangle. So you can split the trapezoidal. If in case, if you cannot remember the formula or the area formula or centroid of a trapezoidal, you can always have the option of splitting this rectangle and triangle. Otherwise, you can treat this as a complete trapezoidal. In the previous problems which you have solved using the other method also, I've split this here, rectangle and triangle. Okay, so let's solve this problem using the trapezoidal formula. Okay, so now area of a trapezoidal, it is A plus B. So it's A smaller distance, A small ordinate plus big ordinate, A plus B divided by 2. A plus B divided by 2. So that's how it is. Theta C area. So area of a trapezoidal, A plus B divided by 2 into this side. Okay, it's there 16.2 plus 37.8 into height. So the area of this is h by 2 A plus B. So A plus B into h by, this is h by 2. So you solve this, you'll get this theta C. Similarly, delta C. So delta C is this portion. Delta C in real beam is equal to bending moment at C in conjugate beam. So bending moment at C in conjugate beam is again to the left side. See all the loads. So this is area into its CG distance with respect to C. Then area of a trapezoidal, again it's CG distance with respect to C. Okay, so area, see now we have already calculated area, so we'll always take this. Things become simple because we have already solved this. So solve them. When you're solving them, this step is very, very important because those are the values which we'll be using here instead of again resolving. So area of a triangle, I've written here area into its CG distance. So with respect to C, so with respect to apex, it is 3/4 of 1.8. It is 3/4 of 1.8. Then plus next this distance. So again, you have already calculated the area here, area. Then you have to only calculate the CG. So it is 32.4 divided by EI is the area into CG distance. So CG distance is first only the centroid of a trapezoidal first. So centroid of a trapezoidal is H, this is H by 3 A plus 2B, 2 times this A 16.2 plus 2 times 37.8 divided by 16.2 plus 37.8. So the formula goes like this. For if you want to find the centroid of a trapezoidal, H by 3, then open the bracket, A plus 2B divided by A plus B. So that's how we have written here. H by 3, A plus 2B, A plus B. Then because you're measuring this, okay, see here, because you're measuring this with respect to C, so you have to add this 1.8. So I've added here 1.8 plus H by 3, A plus 2B, A plus B. So when you solve this, you'll get delta C. So it's a trapezoidal formula. So if you're comfortable using the trapezoidal formula, you can use. Otherwise, you can always split that into a rectangle and a triangle. Okay, similarly, you have to find theta B now. By finding theta B, so always you should check the loads which are acting only to the right side. Okay, as here, because shear force is acting here at this portion, always free end, the shear force is acting. So when you're finding this theta B here, so consider forces only to the right side. That means consider the area only to the right side. So theta B is equal to shear force at B in conjugate beam. Okay, shear force at B. So it is half into base 1.8, height 16.2. So half into base into theta B. Next, delta B. So delta B in real beam, delta B in real beam is equal to bending moment at B in conjugate beam. So bending moment at B in conjugate beam. So area we've already calculated here. Then from this portion, if you measure, it is 1/3 of the base. Okay. With respect to, we are measuring with respect to B. Okay, so if we are measuring with respect to B means you have to measure from this triangle measured from this side. So it is 1/3. So 1/3 of the base. So 1/3 of 1.8. So when you simplify this, you'll get delta B. Okay. Similarly, you have to find out slope and deflection. So next type of problem, slope and deflection at the free end. Okay. So AB is a fixed AB, end A is fixed, B is free. So it's a UDL. And in addition to the UDL, there is also a point load acting at B. Okay. So first thing is draw the deflected shape of the beam. Then end A is fixed, so no rotation, no deflection. End B is free, so maximum slope, maximum deflection. Okay, after this, because there are two different forces acting here, there's a UDL and point load. So draw two different bending moment diagrams, that is M over EI diagram, followed by you'll have this conjugate support. You can add that later. So first draw the bending moment diagram or the M over EI diagram. Okay, now see here, first for the point load. So consider only the point load. So 25 into this distance, 25 into 3. So at B, it is a free end. So bending moment B is 0 and maximum at A because fixed end. So 25 into 3 is 75. So 75 over EI. And because it is a point load, so draw a linear line like this. Next, bending moment due to UDL. So bending moment due to UDL is 20 into 3 into 3 by 2. So 20 into 3 into 3 by 2 is, when you solve this, you will get here, that is bending moment at A is, now see here, there is a bending moment due to UDL, 20 into 3 into 3 by 2. So at B it is 0 and at A it is maximum. Okay, so it is a maximum, that is 90. And because it is a UDL, you have to draw this as a parabolic curve. You can see here, if you find out the bending moment totally here, if you find the bending moment totally, so you'll get to know that, so you'll get to know when you add this here, 25 into 3 is the bending moment due to the point load. Then 20 into 3 into 3 by 2 is the bending moment due to UDL. So when you add this together, so it will be 165. Now you can always cross verify this, 90 plus 175. When you add this bending moment due to point load and bending moment due to UDL, so you'll get the same answer, 165. Okay, next. Now we'll apply the principle of superposition, or we'll use the formula. That is, first one, theta B in real beam, theta B in real beam is equal to shear force at B in conjugate beam. Shear force at B in conjugate beam. So here, now here, fixed becomes free, free becomes fixed. Now see here, it is to make things convenient for us, we're going to draw the separate diagrams, but actually here the shear force is only at support B, so no need to draw or show here VB. So if you show this at one point is enough. Show both the supports like this as fixed support and show only one force here, VB. Okay, so now theta B. So theta B in real beam, theta B in real beam is equal to shear force at B in conjugate beam. Now there are two diagrams here, so two bending moments. So find the area of this. So it is acting downward, area, the force is acting downward. So area of a triangle, half into base into height. So this is the area of a triangle. Now because it's a UDL, so it's a parabolic curve. So it is 1/3 of base into height. So 1/3 of base into height. So when you solve this, you'll get theta B. Similarly, calculate delta B. So delta B is equal to, again, area of a triangle into its CG distance with respect to B. Again, area of a parabolic curve with then into its CG distance with respect to B. Okay, so now theta B in real beam, the delta B in real beam is equal to, delta B in real beam is equal to bending moment at B in conjugate beam. So you have to consider both the diagrams now. So here you have already calculated the area here. So this area of a triangle into CG distance with respect to B. So again, CG of a triangle measured from the apex of the triangle is 2/3 of the base. So 2/3 of the base plus, next, this area of a parabola is this thing, 90. Again, it's CG distance with respect to B. Again, you're measuring from the apex. So it is 3/4. So this is 3/4 of the base. So solve this, then you'll get delta B. So delta B is 4. Now here also the answer is positive. That means rotation is clockwise, that is movement is clockwise. Here also the answer is positive. That means the movement is, that is the deflection is downward. So you can see that this deflection is downward and this rotation is clockwise. Okay, these are the different types of problems on conjugate beam. So with this, we'll wind up the conjugate beam method. So the next type of next module will be continued in the further videos. Thank you.